Current slide. And while we're waiting on the projector to come on, let me say a couple of things. One very practical thing. I don't know if you remember last time, those that were here, my computer started sort of strobing on me. What we have is a bad connector here, and they can't do a thing with it, so they're going to try to get me a new laptop, but I need one with an ionizing pen to use this stuff. So they're working on that for me. They said they didn't think they could repair it without tearing something else up. So anyway, I'm stuck with this for now. The last class it started doing it, whereas on last Wednesday it only started in this class. But it's eased up now and is doing much better. But hopefully it'll continue that way. So that's the practical thing. Another one that's fairly practical, and I don't recall because it's been a while since I entered your attendance. I don't know how many of you have completed payment and how many have not. But at some point coming up, I'm sure fairly soon, and we never know when, they just decide to remove unpaid students from the classes. When they do that, generally you can get back in, but you got to convince them you're going to pay. So it's a lot better to go and get it taken care of now. Or if you are waiting on something, let someone in the business office know so they can kind of flag their flags to let them know not to remove you from the class. So for those who haven't. Now, here's the next thing, and this is a bit more personal for me anyway. I don't know if any of you are ever even think about coming by for office hours on Tuesday or Thursday. Because you see, I have almost no office hours on Monday or Wednesday. I have 30 minutes at the beginning of the day, 8 to 8:30, and I have 35 minutes at the end of the day at the end of this class, 5:30 until 6 o'clock, 5:25 until 6 o'clock. So that's a big 65 minutes of office hours on Monday and Wednesday. Y'all can catch me at the end of the day, that middle class, at 5 minutes on either side, and that's all. So, but if you ever thought of coming in on Tuesday and Thursday, have big chunks of office hour, 10:45 until 4:30. Okay, nice chunks there. I'll be here tomorrow for that nice big chunk of office hours, but on Thursday I will not be on campus at all. I've got to have my cataract surgery on my left eye, and usually they start pretty early in the morning. They haven't let me know when to come yet, but they usually start you very early in the morning, and then you're pretty much done for the rest of the day. They finish relatively soon, but I can't do any driving or straining or anything for the rest of that day, and my wife thinks it's even on into the weekend. So she has a bunch of phone calls and stuff like that. She said, you can do that. You can't be working in the yard, but you can do that. So anyway, I will not be on campus, on either campus at all, next Thursday. I will tomorrow, but not on Thursday, this coming Thursday. So if you were planning to come see me, don't bother on Thursday. Come see me tomorrow, but not Thursday. All right. I guess that's all the announcements. Any questions on anything we've covered so far? All right. Where we left off, we're on in Chapter 12, which is vector value functions. 12.3 is velocity and acceleration. And example 6 is the one right here. And this makes pretty good sense. A baseball is hit 3 feet above the ground. That's just about the sweet spot, just about level, okay, above the ground at 100 feet per second. I guess that's making sense. It sounds like you hit the baseball at 100 feet per second, like you might be going, but no. You hit the baseball and give it a speed of 100 feet per second at an angle of 45 degrees above the horizon, with respect to the ground, so above the horizon, as shown in this figure. Find the maximum height reached by the baseball and answer this question: will it clear a 10-foot high fence 300 feet located from home plate? And obviously, this is not drawn for scale, but it's far better than anything I would have drawn, so be thankful for what you got. Okay. Now, if you think back, here was our position vector for a projectile. R of t v naught cosine theta t I plus h plus v naught sine theta t, this is a constant, times t, that's t squared j, where g is the acceleration coming 1/2 gt squared, where g is the acceleration due to gravity. Now, with that in mind, let's think back here, okay, and identify some of these parameters, okay. V naught here, obviously, let me get my pen set up. Anyone tell me what V naught would be? 100 feet per second. So here is the V0, 100 feet per second. Okay? Theta. That's your 45. Okay? T is your variable, the time. H. That's your 3. Here is your H. Okay? V naught we already had, sine theta we already have. And the G, since you're measuring in feet per second, that kind of stuff, what will your G be? GBs. Anybody remember? No, 9.8 if it was meters. Feet, 32. I say 32 and write 33. I don't know what's wrong with the brain here. Okay. 32 feet per second squared. There's your G. Okay. Now, the first question says, find the maximum height reached by the baseball. So here, go back here, and what relates to the maximum height of the baseball here? Is it the I part or the J part? The J part. Okay, and the maximum height, that would be, all right, Rachel, right? Okay. Even half dozen now. Okay. Maximum height would be where, what would be true about maximum height of this? How would that relate to the function here? It's true about the maximum height. Maximizing function. We did this sometime back in Cal 1, right? Second? What kind of shape is this? Maximum point is 2. Your variable is t here. That's a constant. Variable. Parabola. What's true about up here? Again? It's the highest point, vertex we sometimes call it. What's true about that and a good calculus term? Okay, tangent line. Huh? What is equal 0? Slope of the tangent line. What relates to the slope of a tangent line? You're like a dentist pulling teeth here. The first derivative is 0, of course. So let's take a first derivative of our j part of the function here and set it equal to 0, if I can turn in the right direction here. Good deal. This is Tevin, right? Okay. All right. We are filling up a little bit. Okay. So let's write down that j part there. let's call it y if that's okay. Y is equal to h plus v naught sine theta t, right? V naught sine theta t minus 1/2 gt squared. Okay, now, would you rather take the derivative of this or plug in numbers and have numbers in there? I really don't care too much. Anyone have an opinion? Plug in numbers? Okay. The h we said was 3. All these are feet. Plus the v naught was 100. The sine of 45 is, we know that one, don't we? Sine of 45? Second? No, it's root 2 over 2. Okay? So it's root 2 over 2, and that's times t minus 1/2. And what was the g? (32). I'll leave off the units for now. T squared. Okay? Let's clean that up just a little bit. 3 plus 2 will go into 100. 50 root 2 t minus 16 t squared. That was the y, or height, as a function of time. And what did you suggest we do to it? Take a derivative. So y prime is equal to 50 root 2 minus 32t. Okay? Now, setting that equals 0 gives you a time. That's the time at which it reaches its maximum height. Doesn't tell you what the maximum height is, but it gives you the time that it reaches it. Okay, assuming t equals 0 is when it did. So if you set this equal to 0, then that means that 32t is equal to 50 times root 2. Everybody agree with that? I just moved one from one side to the other. Okay with it? Okay. Now we can divide, well, let's divide everything by 32. And 2 will go into this 25 root 2, and 2 will go into this 16. Okay? So with your calculator, figure out what 25 root 2 over 16 is. That will give us a time of maximum height. (25 times root 2 divided by 16). Probably something more than 2 seconds. Probably less than 3, I'm guessing. Second? 25 root 2 divided by 16. 2 point what? 2.20. Okay. Now that gives you the time it reached the maximum height. To find out what maximum height that was, plug that back into your original function. Okay? But we can do it on this one down here if you want to, because we've already done that. Or actually, this one down here would be the best, I guess. So plugging in 2.2 there, you have the height, or the y value, at 2.20 seconds will be 3 plus 50 root 2 times 2.20 minus 16 times 2.20 squared. All right. With your handy dandy calculator, tell me what that is. 81.3? Is that what you said? 0.12? 81.12, and that would be feet. Okay? Because this would be, that's in feet, this is in feet per second, times seconds would be feet, and this is feet per second squared, times second squared would be feet. So 81.12 feet. Pretty high. So we got that answer. The question is, will it clear a 10-foot high fence located 300 feet from home plate? Well, what we've done so far won't really tell us that answer. What does the 300 feet represent here? That's going to be your x-coordinate, isn't it? So we need to figure out when the x-coordinate here is 300, what time would that be? Okay? Does that sound right? And then plug that time into the y-coordinate and see what height it would be. Making sense? And then you'll know, did it clear the fence or not? Okay? So we want V0 cosine theta times t. Oops, I went the wrong way. V0 cosine theta times t. We want that to be 300 and see at what time that happens. So the t would be equal to 300 divided by V0 was 100. And what was cosine of 45? Root 2 over 2. So I'll put the 2 down here and the root 2 up there. Is that okay? Okay. 100 will go into 300 3 times. So 3 root 2, 3 halves times root 2. So 1.5 times root 2. About what time would that be? Say that one more time. 4.24. That would be seconds. Okay? Let's see if when you plug that into your y, which again is this thing right here, how high will the ball be? So plugging that into y at 4.24 would be 3 plus 50 root 2 times 4.24. So 2 is an ugly 2. Minus 16 times 4.24. I'll leave off the seconds for now. Squared. Okay, so if you can read that ugly writing. 3 times 50 root 2 times 4.24, I think is what you said, minus 16 times 4.24 squared. Second? 15, so your y would be about 15.17 feet. Well, let's see. I think that even with a great outfielder out there pushing off. I don't even think he could reach the top of the wall, stretching, jumping as high as he could, not going to get up 15 feet high. I think that ball's out of here. Okay? What do you think? They just round to 15, which probably is safe. Okay? And the earlier thing was 81 feet, which I think is pretty safe too. I know I wrote it somewhere here. There it is, about 81 feet. Because you really only have two significant digits, you don't even have two of everything here, but we'll just settle for two. So, maximum height, about 81 feet, and it does clear 15, so good chance no outfielder's going to catch that one 5 feet above the wall. He'd have to be standing on the wall to do that. I don't think that's allowed. Okay, that was the last. Any questions on that? You see how it worked? What the rationale, the reasoning was? Very little calculus required there. Taking derivative was about it. Okay. So, 12.3 exercises. Any of the odds 3 through 9, they're all at Calc Chat. 3 is at Calc View. Any of the odds 11 through 19, they're all at Calc Chat. 15's at Calc View. Any of the odds 21 to 25, they're all at Calc Chat. 21's at Calc View. Any of the odds 27 to 39, they're all at Calc Chat. I don't see any of those at Calc View. Okay. Do number 41, it's at Calc Chat. 43 is at Calc Chat. 45 is at Calc Chat. Either 47 or 49, they're both at Calc Chat. 51 is at Calc Chat. You can explore doing either, if you choose, 53 and or 55. That's up to you. They should be at Calc Chat. 57 should be at Calc Chat. 59 is a proof, so if any of you are math majors, that might be something you want to pursue. If not, just whether you want to or not. And then they have a couple of true faults, 61 and 63. They should be at Calc Chat as well. All right, any questions? Oh, wait. Let's see how they did it. I forgot. You're given the h equal 3, v0 is equal to 100, and theta is equal to 45. Using the theorem we had turned back to with g equal 32 feet per second, which I call feet per second squared. Then you have plugging in what we know. R of t is 100 cosine pi force t I plus 3 times 100 sine pi force t minus 16 t squared, 1/2 of 32 is 16 t squared. And that's all the j part. And that would be, because cosine of pi force is root 2 over 2, this would be 50 root 2 t I plus 3 plus 50 root 2. Again, sine of pi force is also root 2 over 2. So 50 root 2 t minus 16 t squared j. Okay? So that's what we have to work with. The velocity vector is the first derivative of the displacement vector, and they use both the I and the j components, though they really don't need the I, the I component that much. They just want the j component, but they can have it here. 50 root 2 plus 50 root 2 minus 32 t j. The maximum height would be when the y prime is at 0, so set that equal to 0, and you have t is equal to 25 root 2 over 16, which I think y'all calculated to be 2.21 seconds. I think we just said 2.2, didn't we? Yeah, pretty close. Okay, the maximum height reached by the ball would then be when we plug that in to the j component, 3 plus 50 root 2 times 25 root 2 over 16 minus 16 times 25 root 2 over 16 squared. Okay. All right. Easy enough to, well, just plugging in, nothing really all that easy. But you can divide out certain things like 6. 2 will go into that, 2 will go into that. One of these, this one will go into one of those, and continue with that, and you'll find it comes out pretty much 649 over 8, which is right over 81 feet, approximately 81 feet, a little bit more than that. Now, the ball is 100 feet from home plate where it was hit, and the last part of the problem, so plug that into, you know, the 300 must be root 5 over root 50 over root 2t, I can't talk, and when you plug those values in, you get pretty close to 300. Wait a minute. Oh, I'm sorry. You plug those in, and because you're trying to find out what time it reaches 300, so you divide by 50 root 2, which would be, goodness gracious, 3 over root 2, because 5 will go into 36 times, so that'd be sure there's some way there that they got the 3 root 2, but I'm not seeing it right off the top. 50 will go into 36 times. That'd be root 2t equal 6. Okay. I don't know. My eyes are bothering me, and I can't quite. Part of that is the lights too. So divide both sides by 50. You get root 2t equals 6. So it seems like this should be t is equal to 6 divided by root 2. Yeah, and that works out. Yeah, I see what it's doing now. Multiply and divide both numerator and denominator by root 2. You get that. 4.24 seconds. So then you plug that in to your height, and that will be, again, I'm having trouble with the glare, 3 times 50 root 2 times, they didn't put 4.24, they put 3 root 2 minus 16 times 3 root 2 squared, which that comes up a pretty easy number to calculate, and they get 303 minus 288, about 15 feet, the height when the ball is at 4.2 seconds out. So it will clear the 10-foot fence for a home run. Unless, of course, that was in foul territory. We didn't know that. Okay. And that was it for the chapter. So, I mean, I'm sorry, I can't talk. The section. I'm sorry. My thing has settled down greatly, but it was doing so much strobing for it was just driving my eyes crazy, and now I'm having a hard time focusing because they are somewhat painful. So let's move on to 12.4. Okay. Depending on how we go on this, and this is not a long section, but there's well, it is a fairly long section. And we still got 12.5 to go. I think it'll be Wednesday when we'll be ready for the first test. So let's pick up and go from here. Okay, Chapter 12 is vector-valued functions, and 12.4 is tangent vectors and normal vectors. Now, we've talked about tangent lines. Haven't talked anything much about normal stuff yet, I don't think. I don't recall that we have. So these are going to be sort of some new concepts here, but they're going to come directly from the type of stuff we were doing before we took our time out to do the accelerations and velocities. They relate to them, of course, but that was sort of a sidetrack there. My head's hurting. Lights don't help any. Find a unit vector, a unit tangent vector, and a principal unit normal vector at a point on a space curve. Well, we got to define what these things are before we're going to find them. And then we'll find the tangential and normal components of acceleration. So that's why we had to do the acceleration part, so when we got here, we'd know what we were talking about. So let's start here, and here's some definition. A velocity vector points in the direction of motion, as it always has. So far we've been in basically planar motion. This observation leads to the next definition, which applies to any smooth curve, not just those for which the parameter represents time. Any smooth curve. You're not just talking about motion now, you're talking about any smooth curve. So the definition of a unit tangent vector. Let C be a smooth curve represented by some vector r on an open interval I. Now we don't even know what the independent variable is, but that's going to be on this open interval I. The unit tangent vector is saying not for which the parameter represents time, but we're using time. So the capital T bold is a vector. And it happens to be a unit tangent vector. Now notice here, they just do any vector in bold, and they don't distinguish between vectors. Since I can't write bold, when I'm writing a vector and it's any old vector, I put an arrow over it, okay? But when it's a unit vector, I put a, whatever you call those things, house top, there is a name for it. I put that over it, so I remind myself and you that's a unit vector. So this is a unit tangent vector, so capital T stands for the, bold T is the tangent vector, unit tangent vector. Little t is whatever the independent variable is. It doesn't always have to be time, but quite often it is. Okay? So, the unit tangent vector is defined to be, now, back off for a moment. The tangent vector in any smooth curve represented by r of t is going to be the tangent vector. It's going to be its first derivative, just like it was in 2 space. First derivative gives you your tangent line, But that's not necessarily going to be a unit vector. So how do you get that tangent to be a unit tangent? Is divide by its magnitude. So divide by the magnitude of r prime, that's going to be your unit tangent vector. Direction of motion in with a magnitude of 1. Now, of course, this won't work if the unit tangent vector is a 0 vector. Well, obviously it won't because you're not moving. Okay, so how can you have a tangent? Okay, so any kind of a curve like that, it makes no sense to. If the r is not changing any, then it can't have a unit tangent vector. So r prime cannot be the 0 vector. We know that the curve is smooth on an interval when r prime is continuous and non-zero on the interval. Okay, so we don't want r prime to be discontinuous, and we don't want it to Okay. Is continuous and non-zero in interval. So the smoothness is sufficient to guarantee the curve has a unit tangent vector. So there's our definition. Let's do one. Find the unit tangent vector to the curve given by, here is our curve. This is in 2 space. R of t is equal to ti plus t squared j. And we want to find that unit tangent vector when t is equal to 1. So what do we do first? get my pen set up. Okay, what do we do next? Any guesses? Take a derivative, always a good answer, okay? R prime of t is equal to I, that's yes in Navy, okay, plus 2t j. Perfect. See, unit vectors, I put housetops over them, okay, to remind myself and you they're unit vectors. Regular vectors that are not necessarily unit vectors, I just put the arrow over them, okay? That's a tangent vector, but it's not a unit tangent vector, obviously. How do we get a unit tangent vector? What are we going to need to do? Divide by the magnitude. So that will be I plus 2tj divided by, how do we get the magnitude of that? The square root of 1 plus 2 squared is 4. More. T squared. The t is also part of that. Okay? That is our unit tangent vector at any value t. Okay? They're asking when t is equal to 1. So what is the unit tangent vector when t is equal to 1? I'll do the top part, that's the hard part. You do the bottom part. Root 5, okay? And you might like it a little better if it was 1 over root 5 I plus 2 over root 5 j. Now, being the cynic that I usually am, I like to make sure this is a unit vector. So I'm going to square this, and that would give me what? One over 5 plus 1 over 5 plus 4 over 5 is 5 over 5, which is 1. Yes, that's a unit vector. So sure enough, that will work as our unit vector when t is equal to 1. Okay. Now, they do, I'll let them do the drawing. We're going to stop it here and let them, well, I'll show you how they wrote the answer. Not that it really matters. 1 over root 5 times I plus 2j, which is fine. You just took this one and put the 1 over root 5 in front. But that leads to another issue here. I haven't gotten it set up yet, but I think you have access to it already if you bought the book in the bookstore anyway. The use of enhanced website. Now, I don't know if any of you have used it yet or if you like it or whatever, but when you're running one of those packages like that, they are usually looking for one and only one correct answer. So if you had written this down, but they were looking for this, they tell you that's the wrong answer. It's not. That's a correct answer. It's just another way of writing this. So that's one reason I really don't make any assignments. I'll put them out there, but they're only for your benefit. Don't get frustrated with them and drive yourself crazy with them. But that's what they're doing, is just looking for one particular answer. And especially in calculus, usually a dozen ways to express any given answer. That may be a little bit of an exaggeration, but it's that. Now, let's clean my stuff off the screen, and let's see how they work the problem. First thing they did was just like you. They took a derivative, I plus 2tj. Boy, this glare is just driving me nuts. Okay? So the unit tangent vector is to take that vector and divide it by the magnitude of itself. That's the definition of unit tangent vector. So the magnitude of this would be square root of 1 plus 4t squared. So that's in the denominator times this, which is in the numerator or off to the side or wherever. And then for t is equal to 1, that would be 1 over root 5 times I plus 2j. Now, the unit tangent vector here, it looks like they got it right. There's some measure to the right, and then quite a bit higher to the double that up. And that's the unit tangent vector. There's also a tangent vector coming down this way, but this indicates the direction of increasing t. The unit tangent vector is the direction of movement from t to a low number to t to a higher number. So that tells you it's moving that way rather than down. Okay? On this side, that t would have been like this. Okay? It's coming down. And that's what they're mentioning at the bottom of the page there. The direction of the unit tangent vector depends on the orientation of the curve. All right. Yeah. Now, the tangent line to a curve at a point is the line that passes through that point is parallel to the unit tangent vector. In example 2, which we're about to do, the unit tangent vector is used to find the tangent line at a point on a helix, which is a spiral, sort of slinky type thing moving up. Okay, here's example 2. Find the unit tangent vector as a function of t, and then find a set of parametric equations for the tangent line to the helix given by, a set of parametric equations for the tangent line to the helix given by r of t. The helix given by this. So, and this is at the point root 2 pi fourths. Okay? Now, before I do anything else, no, I guess we're okay. I think I do want to do this. I want to make sure this point is indeed on that curve. Okay? Now, the easiest place to begin, because this involves with the cosine of t, and that's going to be fairly easy to deal with. The sine of t will be fairly easy to deal with. But this is the easiest thing to deal with. tk indicates this is the k component, right? So t's got to be pi fourths. So let's go back and plug in pi fourths here. Cosine of pi fourths is, anybody? Root 2 over 2. Multiply that by 2 and you're left with just root 2. Sine of pi fourths, root 2 over 2, 2 times, you'll divide out that, so that's again root 2 and pi fourths. So yeah, that point is on that curve at a given t equal pi fourths. Okay, that's just because I'm a little paranoid about it. They may give you a problem that makes no sense because it's not even set up properly. So, find the unit tangent vector, and then we'll find a set of parametric equations for the tangent line. So what's the unit tangent vector? Where do we begin? Take a derivative, and that will be I'm sorry, I can't hear. Okay, I hear something, but I can't make it out.
2 sine.
Okay, isn't it a minus 2 sine? Okay, minus 2 sine t I plus 2 cosine t j second plus k. Perfect. All right. Man, hold on just a minute. My eyes are just giving me huge fits here. Last class was nothing but a strain. Just about, well, at least half the class. My screen was just strobing on me. All right, so what do we do with that? There's our first derivative of the displacement vector, which is a tangent vector. But what are we looking for? Second? Okay, we're going to be there in a minute, but what do we have to find first? T of t, okay? That's the unit tangent vector. How is it related to the first derivative of the displacement vector? Definitely related. How? Anybody? A little louder? Okay, divide by the magnitude. Let's first find the magnitude r prime of t. And that would be what? Oops. Okay, I was waiting for an answer and my pen touched the page and drug. I can't get it to erase now. Well, everything except what I want to erase is erasing. I don't know why. Okay, there it disappeared finally. All right. What's the magnitude of that vector there, r prime of t? I got the first part, the square root. What's the next part? Okay, 4 sine squared. Is that what you said? Say yes. Okay. Square this one, and that gives you 4 sine squared t plus 4 cosine squared t plus what? Just 1. The coefficient. The magnitude of that vector. Of the k component is just 1. Right? 1 squared is 1. Okay? Now, what do you notice about those first two terms? The what? Okay, well, yeah. We can factor out a 4, and that leaves us a sine squared t plus cosine squared t, close parentheses, plus 1. And this would be, as you said, this thing is now 1, so this would be the square root of 4 plus 1, which is square root of 5. So there's the magnitude of this vector, And notice it has no t dependence at all. They just disappeared with sine squared and cosine squared. So this is a constant magnitude. So now going back to what we're looking for, what is your t unit tangent vector? What would it be? Second? Okay, we'll take this vector here, and the way they did it last time was just put 1 over root 5 out in front times minus 2 sine ti plus 2 cosine ti. I said I mean J. Goodness gracious. I put parentheses on one but not the other. Let's see if I can get these off. Okay. Alright. Plus K. I am so sorry, but my eyes are giving me fits. Part of it is cataract and part of it is strobing that the computer was doing earlier. Just alright, so this is the unit tangent vector. It's the derivative of the displacement vector divided by the magnitude of that. So I'll just put this up front. So that's what it is. Now, well, that's at every point t. Says, so we found this unit tangent vector. Says, then find a set of parametric equations for the tangent line to the helix given by that. Okay? Now, I was looking at the wrong problem. I said, how did they get that mess? Okay? 1 over root 5 negative 2 sine t. Right. Okay. Okay, I've not read the problem far enough. So we found this part. And it says, then find a set of parametric equations for the tangent line to the helix given by this. So I just sort of stopped there and thought, how can you do that at this point? No, at this point, which we've already verified is on this. So we want a set of parametric equations for the tangent line to the helix given by this formula here at the point here. We've already verified that point's on there. So a set of parametric equations for that tangent line to the helix there. Goodness, my nose itches. Okay. So at this point, all we do is plug this value here into, well, all right. Basically, what we're saying is I keep looking at the wrong page here. We take this value here, unit tangent vector of t, okay, it just seems like it's a little backward the way they do it. What you do is find out the t first, and that's what we did before, okay? And, well, I'll leave it for now. Okay, no, I don't think I will. Okay. This thing gets a little crazy. Okay. All right. All right. Now, as we said before, this is true when t is equal to pi fourths. That's the point that you get when your value of t is there. So when t is pi fourths, plug that in here. T unit tangent vector at pi fourths will be what? 1 over root 5 times minus 2 times what is the sine of pi fourths? I think we've done it already today, at least once. Root 2 over 2 plus cosine of pi fourths root 2 over 2 j plus k. All right, now these 2's will go out, and basically what we have left is the unit tangent vector at the point pi fourths, t is equal to pi fourths, and that's what they're looking for here, is minus root 2 over root 5, I'm just going to write minus 2/5, the root 2 of 2/5, that's the I component, plus square root of 2/5 j, they don't like you writing that, plus k. All right. Now, that one I want to also make sure is no, I'm sorry, 1 over root 5k, because that's still divided by root k. I was going to say that's not a unit vector anymore. But let's see if it is now. What's the square root of that? Okay, what's this square? 2/5 plus 1/5. 4/5, 2/5 plus 2/5 is 4/5 plus 1/5 is 5/5. 1. Sure enough, that's still a unit vector. So that's the unit tangent vector at that value, at t is equal to 4/5. So what they're saying is find a set of parametric equations for the tangent line to the helix given by that equation at the point there. So we want to do is find a set of parametric equations for the tangent line to the helix at that point. Now, that probably takes you back at least to chapter 11 or somewhere there. I keep looking at the wrong page here. They pull out the root 5 in front, which is fine. It doesn't matter. So the direction numbers here and I really do want to take you back where you need to be. I believe it was chapter 11. Let me see and make sure. Okay. May have been earlier. Should have looked this up before, but I just didn't have time. Here we go. Here we go. I think. Well, it's closer. God, this is taking way too long. Ah, I'm missing it. Seemed like it was before this. I'll have to let you look it up, I think. Ah, here we go, got it. 11.5, I was thinking it was before this. Parametric equations of line and space, this is on page 787. If you got this book, or any book that you got, somewhere you'll find this in the chapter on vectors in the geometry of space or some title like that, and if you lines in space, okay? And a line parallel to a vector, if the vector is angle brackets ABC, A is the X component, B is the Y component, C is the K component, the Z component, okay? A line parallel to that vector ABC and passing through some point P of X, I think they call it X sub 1, Y sub 1, Z sub 1, okay? Is represented by the parametric equation X is equal to X sub 1. This is a 1 here. It doesn't look very good. Goodness gracious. The pen isn't writing very well. X sub 1 plus AT, Y is equal to Y sub 1 plus BT, and Z is equal to, don't need a comma, I don't know how that got there. Okay, let me get my pen back. Goodness, my eyes giving me fits. Z1 plus CT. Okay, now that's just our reminder back in section 11.5, lines and planes in space. Those, now they call those A, B's, and C's your direction numbers, okay? Okay. Oh my. Ugh. Now, what we have here is the point. That's our x1, y1, z1. Those coordinates there. That's the point, at the point, okay? And your direction vector are your components of the t vector, which are those. Root 2 fifths, and root 1 fifth. Or, as you want to say, 1 over root 5 times root 2i root 2j plus k, okay? However you want to phrase those. Those are your, what is the A, B, and C. These are your x1, y1, and z1. So what are your, goodness gracious, parametric equations? X equal, your x1 is root 2 plus root 2, I like to write it root 2 fifths, in the I direction. No, I'm sorry, giving parametric equations now, no longer have that. So there's your parameter t, or whatever you want it to be. Now they already were using t down here, so if you wanted to use s you could, and that's what they do in the book. S, your y is equal to root 2, because that's the same value there, root 2, plus, and it's the, now I'm sorry, I messed something up there. That's supposed to be a minus on that one, I'm pretty sure. Okay, let me check and make sure I didn't make another dumb mistake here. No. Yeah. That's a minus on the first one, so that's that. This is a plus on the next one, plus root 2 over 5 t, and your z, I'm sorry, s. We're using s as a parametric equation. All right. Pi fourths. Goodness gracious. Okay. Plus 1 over 1 over root 5 or square root of 1/5. It doesn't matter. I think I actually like it better a little bit, square root of 1 over root 5. Though it doesn't quite match the others. S. So there are the parametric equations. You actually have an infinite number of them. These are the simplest ones to do. Root 2 all right, now I included the root 5, and like I said, you could include, you have an infinite number of them. But since these are common to all those, you could just make it root 2s, and s. And that's what they did in the book. Not that it's any better, but it's I guess, easier to write. Root 2 minus root 2s, root 2 plus root 2s, and pi fourths plus s. So basically, for this part here, they just took out the root 5s, which is fine. I mean, they don't really contribute anything. They're just the multiples of that, but it can be any multiple of that. And that just, if this is your point, the root 2's may take you this far, without the root 2's it may go that far, or this far, or that far, but you're all on the same line. So these are parametric equations. They aren't the only set. Okay, now, I think that's all we had to do on that. Let's see how they did it, which means clearing out what I did and proceeding. Derivative of r of t is, r prime of t is minus 2 sine ti plus 2 cosine tj plus k, which implies that the square root, the magnitude of that would be the square root of the first component squared, 4 sine squared t plus 4 cosine squared t plus 1. Okay? Notice common factors here are 4, so pull those out, and that gives you a sine squared plus cosine squared. And they really need a break, so that they got a, this gave them 1, it's the square root of 4 plus 1, square root of 5. Okay? It's really simplified. Therefore, the unit tangent vector is that unit, the tangent vector divided by the first derivative vector divided by its magnitude. So it would be 1 over root 5 times minus 2 cosine, or sine t j plus 2 cosine t, said j first, minus 2 sine ti plus 2 cosine t j plus k. Okay, at the point where root 2 pi fourths and t at the point root 2 pi fourths. Oh, okay. I kept wondering why they put another comma here. That is to separate this from this. At this point, t is equal to pi fourths, because if you went back to your original equation, your r, t was pi fourths at that point. We already determined that. We did that very early on. And the unit tangent vector there would be, at pi t equal pi fourths, would be 1 over root 5 times negative 2 root 2 this because you plug in so running out of energy. Pi force here, and that would be sine of pi force is root 2 over 2. So minus 2 times root 2 over 2i plus 2 times root 2 over 2j plus k. So there's your unit tangent vector. Of course, the 2's here divide away in both instances here. So that leaves you with is 1 over root 5 times minus root 2i plus root 2j plus k. All right. Now, using the direction numbers, and now what I used as direction number was root 2 over root 5, root 2 over root 5, and 1 over root 5. See, you just need numbers. They don't have to be normalized numbers. Any number, root 2, or negative root 2, root 2, 1. That works just as well as dividing by each one of those by root 5. So they just use those, negative root 2, and c as your direction numbers. The point that they were already given us is this: you can obtain then the x is equal, and this is what we got from back in 11.5. This glare is killing me. This would be root 2, or I'm sorry. No, that's okay. Root 2 minus root 2s. All these root 2's have getting them confused. Where s is the new parameter, not t. They just chose to use s because they'd already used t. Root 2 minus root 2s. The y parametric equation would be y1, which is this value, plus root 2s. So that would be root 2 plus root 2s. And then the z1 would be pi force plus c times s. Okay? Now, I'm sorry. cs, and this would be equal pi force plus s. Okay? I forgot they were doing an extra step, but pi force plus s. So those are your parametric equations. You don't need the root 5's in it, but it doesn't hurt to have them in it because they're always in the same place. Okay. Now, here is a picture of that. Okay, it starts at 2, 0, 0. Okay? And t is equal to 0. This is 2, that's 0, and that's 0. Okay? And then it starts going up the helix. Okay, it just keeps climbing. T is equal to pi force, you're right here. X component is 2 times root 2 over 2, so that leaves you just a root 2. Well, I mean, this is what they gave us, root 2 pi, and sure enough, that's on it. And the tangent line to the curve at the point is the terminal of the unit tangent vector at that point. So there's the unit tangent vector there. And then when you plug in the parametric equation, it gives you every point on that line that goes through that point with the in the direction of the unit tangent vector, which we don't have there, but have elsewhere. Okay. Now, in that example, there are infinitely many, like I was saying, vectors that are orthogonal to the unit tangent vector. Oh, okay, this is something new. Okay, let's go back here. Here is a tangent vector. This blue line here is a tangent vector. It's not a unit tangent vector. That would just be a fixed length 1. That would be something like that. But orthogonal to that, any vectors you do here would be orthogonal to that. All it has to be is perpendicular to that line. So as long as your perpendicular line go all the way around there, infinite number of of lines that are perpendicular to that line. Okay? Infinitely many vectors orthogonal to the unit tangent vector. One of those is the unit tangent vector prime, the derivative of that. Okay? Now, why is that the case? Well, if you were to do a dot product with the unit tangent vector and itself, okay, that is a definition of the magnitude of that square. But you know this is a unit tangent vector, so its magnitude is 1, square 1, you still get 1. And then they jump to that, okay, and that's certainly true. And here's how they got it. I mean, they skip a bunch of steps here. You know that this is equal to 1. So if you were to take a derivative of this, that's a product rule with dot products, and that would be t dotted with t prime plus t prime dotted with t. Okay? Well, that would be 2 of t times dotted with t prime, and derivative of this is 0. So divide both sides by 2, and you get t dotted with t prime equal to 0. So what does that tell you? That tells you that the unit tangent vector and its first derivative are always going to be perpendicular to each other. So therefore, that's one of those vectors that was this one right here. Now, let me say this before I forget to say it. This is a unit vector. So if I were writing that, I'd put a house top up it. Okay? However, its first derivative is not guaranteed to be a unit vector. It's the first derivative of the unit vector, but that doesn't mean it's a unit vector. So when I write this one, to keep from confusing it, I would put an arrow over that because it's a derivative of it, which isn't necessarily a unit vector. The unit tangent vector is a unit vector, but its derivative is not necessarily. So, anyway, by normalizing then that unit tangent, the first derivative of the unit tangent vector, you obtain a very special vector called the principal unit normal vector. It's perpendicular to the unit tangent vector, and they call it a principal unit normal vector. It's a unit vector because you divide it by the magnitude of t prime. That's what they mean by normalizing it, dividing by its magnitude, make it a normal or unit vector. The normalizing, now they're calling it a normal vector too. That's sort of a little confusing, but it's okay. As indicated by this definition, and here it is. Just like we took the first derivative divided by its magnitude, that gave you the unit tangent vector. What we're going to do now is take the first derivative of the unit tangent vector and get t prime divided by its magnitude, and that gives you what they call the unit normal vector, because you know that this one is normal to the tangent vector, meaning perpendicular. Okay? So this will be a unit vector that's perpendicular to that. Now that's not all, okay? There will be more characteristics of this, and those are forthcoming in a bit. So let's first do what they tell us. This is example 3 on page, goodness gracious, my eye is aching, 847. We got to find the unit normal vector, and then it, when t is equal to 1, for the curve represented by this. Now, we're doing steps on steps on steps. We got to do everything we did before and carry it yet some more. What's the first thing we're going to do? Take a derivative, okay? R prime of t. And what's that? 3i plus 4t j. Now this is in a plane, so this is pretty easy, hopefully. All right, and what do we do with that? Hint, hint. Find its magnitude of r prime of t. And what would that be? Okay, 16 t squared, right? Because you square the variable as well. Okay, 16 t squared, square root of that. That's the magnitude. And why did we do that? Okay, then you'll do your unit tangent vector is the quotient of those two. So I'm just going to put this out front. 1 over the square root of 9 plus 16t squared times 3t I'm having trouble seeing. Goodness, my eyes ache. That's 3i. That's what I thought it was. I just can't see it. 3i plus 4tj. Okay. That is a unit tangent vector. Now, I'm not going to prove that's a unit vector because the next thing we're going to do, well, not yet. Let's continue. How do we get, and boy, this is really dragging out too. Okay. What we've got to do next is take a derivative of that. And this is where I said I'll leave off the hats. Because when you take the derivative of a unit vector, you're not guaranteed to have a unit vector anymore. So I'm going to leave off the unit sign because this one probably isn't a unit vector. Now this is somewhat of a pain, but it is doable. Okay. We're wanting to take the derivative of this. So what I think is a decent idea is go on and combine these two. It's 3 over this thing. Let me write this another way. Hopefully this will be helpful. Here's the unit tangent vector is equal to 3 times 9 plus 16 t squared to the 1/2 power. Isn't that, I'm sorry, to the negative 1/2 power. Okay, I've just written that rather than this in the denominator in a radical, write it 9 plus 16 t squared to the negative 1/2 power. Okay? And that would be I plus 4 times yuck. This is my head hasn't bothered me this much and I don't know how long. 9 plus 16 t squared to the minus 1/2 times t. The 4 and then t is still in there. And this is j. Okay, this is your I component. Now I don't know if you find this any easier or not. To me it's a little bit easier to take a derivative in that form. Okay? So, taking the derivative of this will be a minus 1/2 times 3. That's minus 3/2 times 9 plus 16 t squared to the minus 3/2, right? Derivative of a power is an exponent times the coefficient times the base, drop 1 power, minus 1/2 minus 2/2, which is minus 1, is minus 3/2. Okay? But you got a chain rule here, times 32t. Now, that's why I'm doing it this way. It's easier to me to follow. Maybe it's not for you, but for me it is. And this is all the component in the I direction. Okay? And we'll do the same type of thing in the J direction. Oh! And this will be negative 1/2 times 4, which will be a negative 2. So I think I'll put just the minus sign there. I might regret it later, but I'm going to do it now. Minus 2, I'm going to put my brackets in front of it. Maybe not. That could mess me up, so I'm going to leave the brackets off for now. Because it's minus 2 times 9 plus 16 t squared to the minus 3/2, just like before. I'm sorry, probably would have been a good idea, and I think it is a good idea, to write this t with that 4. Okay, that makes it easier to see. So let me go back and start over on this one. What we have here, besides the failure to communicate, is a product rule. So let's do, I'm going to put the plus here and then I'll put everything in parentheses. I think that'll be a little easier. Okay. You got the first times the derivative of the second plus the derivative of the first times the second, right? Or however you want to say it, that's what it gets there to being. I think I will do the second times the derivative of the first first. So that leaves me off with a plus. Derivative of the first is 4 times 9 plus 16 t squared to the minus 1/2. Okay, that's the derivative of the first times the second plus, but I'm going to put a minus there because it's going to turn minus, the first, which is a 4t, times the derivative of the second, which is a minus 1/2 9 plus 16 t squared times, to the minus 3/2 times 32 t. Okay, it looks like a 6. All right. All that is times j. Now, obviously, you're running out of room really miserably here. Okay. So this t prime of t, let's combine anything we can here. 2 will go into 32 16 times. 16 times 3 is a minus 48 t. I'm going to put this back downstairs here. 9 plus 16 t squared to the 3/2 power. Moved it downstairs. This will be my I component plus four over the square root of 9 plus 16 t squared minus, I have a, okay, the 2 here will go into that 16 times. 4 times 16 is 64 t squared over 9 plus 16 t squared to the 3/2. And that's times the j component. All right, let's see. Okay, we've been at it more than half the time, right? Do y'all need to take a break? Because I see people leaving like they do have to. I hate to teach when they're not in the room. This is an awkward place to end this, but since we've just had a couple people go out, let's stop here and let them come back. You can get up and move around too. I need to get away from the screen because it's killing my eyes. So I'm going to put this on pause. Yeah. Okay. Now this is really turning into a pain in the neck, if you haven't noticed yet. Here is your all right. I'm trying to follow in the book. It seems like they've used some shortcuts. Sometimes their shortcuts are awfully hard to find, but let's just make sure we're on the same page here. The t of t is 1 over square root of 9 plus 16, 3i plus 4j, 4tj. Got it. Then they take the first derivative of that and okay. They do it in a different order than I do, but it is the same thing, just to make sure here. They write first the 1 over, well, they write the 4 with the j, this 4 with that j, okay, over 9, the square root of 9 plus 16t squared, okay? Then they go back and do the minus 3 times 16, which is what we've got here. Well, 3 times 16, where I did minus 48t, they keep it separated. They do 16t in the numerator from here. I'm left-handed, it's hard to keep it pointed. The 16t, let's see, where was it? Yeah, 16t from here over this thing to the 3/2 power, which is what we did. And then they put the 3 with the I, and then they do this 4t with the j, and here they have another 16t, and it's also a minus over 9 plus, so they group all those together, okay? Now, okay. And I was proceeding to group the i's and the j's together, which I think are legitimate here, but I wanted you to notice what they pull out, okay? And so I think I will delete what I was doing here because it was not particularly making anything any clearer, and it's just because they knew exactly which way they were heading and wanted it to go. So let's combine a few things here. Okay. All right. You see, this one they have to the minus 1/2. If they made this to the minus 3/2, so in order to do that, they'd have to multiply. I'm sorry, that's not what I wanted to do. And this, it really looks suspicious, but it's true. Okay, multiply this by this on top and by that on the bottom, and now you get a minus 3/2. So what I'm going to do is exactly what I just said, and this looks like it's making it worse, but it actually does make it a little better. 9 plus 16, that's the 16 t squared over the square, okay. They don't use squares here. They use to the 3/2 power. 9 plus 16 t squared to the 3/2 power. Okay. Now the reason for that is now they have this in every term. This is to the minus 16. This, you can put this 1 over this to the 3/2. This over 1 over that to the 3/2. And this over 1 over that to the 3/2. So that's what they've done here, is get them all there. So this yuck has out here at least 1 over 9 plus 16 t squared to the 3/2 power. So that's out in front of everything. Okay? This is a pain in the neck, the way they're doing this. Okay? But there's a reason for it. Okay? Now, they pulled this out, and that leaves us a minus, the minus 3i they're going to leave together. I don't think they put the t with it. I think they leave the 3 together. Yeah. They the minus, okay, again, let me say this. Here's a 16 here, here's a 16 there, and they're going to keep this man. They do so much magic here with it. No. Yeah, they're going to keep the 16t together here and just have a minus 3i, this, and 16t. Okay. So this term is going to have the 16t here, and this is going to be times 3i. Okay. So, oops, a minus. Okay. Believe I got it. Actually, it looks like they lost. No. No, yeah, they got the minus out in front, okay, and a 3i there, okay. There's that, okay. So that takes care of this term. All right, over here they've got a 4 in this same denominator, okay, but the 4 they're going to put with the j, okay, and this denominator, okay. Okay, this is going to wind up being 36 plus 64 here. Well, I'm trying to reconcile the two. The terms are right. Let me just cut to the chase and show how they limit this, because it's to go through every step, because they're skipping steps like crazy, and I hit the wrong key there. I didn't mean to erase it all. Yeah, well, I'm not going to go back and reproduce that. But what we had, just to remind ourselves, the T of T is, and I kind of like the way they wrote this, 1 over the square root of 9 plus 16t squared. And this was 3i plus 4tj. We had that, okay? Maybe not written quite in that grouping, but we had exactly that, okay? So when you took the derivative of it, now this is no longer necessarily a unit vector, so I'm going to not keep the unit vector symbol over it. And I'm going to jump right to the chase and write their final answer. They mixed up the terms i's and j's and just did all sorts of weird stuff with it. But here's what they wound up with. 12, which there is a place where that comes into play here. 9 plus 16t squared to the 3/2 power. Now, I don't like that they're mixing up the square roots when it's 1/2 and 3/2 when it's not, but it's okay. Okay, times, and this is the part that I was trying to figure out, and I was erasing part of it, and I hit the wrong key. This would be a minus 4ti, okay, plus 3j. And at first glance, I thought, how in the world did they get that? But then I saw when they multiplied certain things together, that's what it came up. Now, this certainly looks a lot easier than the long thing that I was writing, but it does combine to be this. And that's why I really hate these, because there's so many different directions you can go with it. But this is what it turns out being. You have to take their word for it, okay? So that's 12 over 9 plus 16t squared to the 3/2 power times 4ti minus 4ti plus 3j, okay? Now, that's what we were heading for when I hit the wrong key and erased. Now we're going to do the magnitude of this, and this is the only reason I did it, to go back and change it, because it makes it much easier to do the magnitude, okay? First, the magnitude of this is going to be just that. That's just the coefficient out in front, so it, in a sense, doesn't go anywhere, okay? So it's going to stay well, they've skipped so many steps. It's really hard to reproduce this. So I think what I'll just do is write down their answers, okay? And it's not intuitively obvious why this is true, but I'll write it down. 12 over 9 plus 16t squared, okay, that is their final answer, okay? And you might say, how in the world did they get this? The 12 stayed alone, but this didn't, okay? Well, part of the reason is that when you're taking the square root of this thing squared, okay, certainly when you square this, you get 12 squared over this thing to the cube power, okay? All right, so that's it. When you take the square root of this, that's the square root of 16t squared plus 9. Well, that's the same thing as this, okay? But this one has it as a 3 has power. That and when you do all this, a lot of things cancel out. Okay, and that's what takes care of the. And this is the square root, by the way, because when you take the square root of this, which is what you're doing, the square root of 16t squared plus 9, okay, which is exactly what this is. That wipes out the square root part, okay, in a sense, okay, and subtracts away a square root of it, and that leads you to the 3 halves minus 2 halves is, minus 1 half is to the 2 halves power, and that's where that comes from. So you see, squaring that, taking the square root of this thing squared, the sum of these squared, gives you this. That wipes out 1 half of those, and that 3 halves minus 1 half is 1. So that's where this comes from then. A much easier way to do it, but wow. You had to know that's what it was coming to in order to see that ahead of time. So it's just really bizarre. Now that you've done that, now you can get your unit normal vector. Oops, it's a unit vector, so I like to put that caret over it. Okay, the unit normal vector is this vector, 1 over the square root of 9 plus 16t squared times 3i plus 4tj, okay, over this thing, okay, which is 12, and then I'm going to move this up here over 9 plus 16t squared, okay. Well, this is going, this square root will move the square root up here, because this is to the 1 half, that's to the 2 halves, okay. And, okay, what it okay, and I wrote this one down wrong. I looked at this one, I should have been looking at this one. This is the minus 4ti here, and the plus 3t, I looked at the wrong one. Minus 4ti plus 3j. It was this thing, the t prime. And I guess I looked at this one wrong too. So let's start this over again. Okay. It's this one. 12 over 9 plus 16t squared to the 3 halves power. Okay. And then you're times this thing here, and then you're dividing by 12, so that goes down here, times 9 plus 16t squared to the first power here, that's this thing in reciprocal. This will wipe out one of those, the 12s go out, and what you're left with is minus 4ti, that's a plus there, plus 3j over the square root of 9 plus 16t squared. Okay, so that's your n of t that they have in the book. Now they just wrote it separate, but 1 over 9 plus 16t squared times minus 4ti plus 3j. Now, that's for any t. When you plug in, what did they ask you for? N of 1. Let's write this up here. Yeah, here's your n of 1. N of 1 is then going to be, when you put t, 1 in for t, you get minus 4i plus 3j over the square root of, this is not going to be readable, 9 plus 16. But what's 9 plus 16? 25. Square root of 25 is 5. So that'll be minus 4/5 I plus 3/5 j. Okay? Now something doesn't, yeah, I think that'll work. Now, is that indeed a unit vector? Well, let's see. Square that. 1625, square that. 9 over 25, 16 over 25 plus 9 over 25 is 25 over 25. Sure enough, that is a unit vector. Okay? So there is your unit normal vector at t equal 1. This is a unit normal vector at any time t. What a pain in the neck that is, but at t equal 1, it's a lot easier to see. So that's why I asked for. Find n of t. There it is. Okay? And n of 1 for the curve represented by that. Okay? And it would have taken probably 3 or 4 screens to have done all the steps there. So I just sort of cut to the chase and went with what they had. Now, thank goodness they do it, so let's take a look and see. Okay? All right, first thing, you take a derivative of this. A long time ago we did that. 3i plus 4tj. Got it. Take the magnitude of that, and that gave us that square root of 9 plus 16t squared that we were using all along. Okay? What do we do with that then? You get the unit tangent vector by doing the r prime over the magnitude of r prime. And that gave us 1 over this times this. Okay? Now, that's the unit tangent vector. To do the derivative of the unit tangent vector is what you've got to do next. Remember what that looks like, and we're going to do a derivative of it. Okay? What they're going to do, split this into 2 pieces. And this is where they just skip steps like crazy. Okay? And I'm going to try to see if I can help you see, and they're on different screens, so it's really hard to do. When you take the derivative of this with the I there, okay, you just get this thing to the negative 3 halves power with a 32t in the numerator times the 3i. So that's a pain. Then you take this one and you have a quotient rule, or if you're writing it a different way, a product rule, and that really expands the terms. Okay? So just telling you, that's how they get these terms, and when you do combine them, and they combine them in such a strange way, you have this one with the j, a 4j, this one with a 3i and a 4tj, okay? This got a t in it, this one doesn't. This is to the 1/2 power, this is to the 3/2 power. It's just really bizarre how they broke this down, okay? Now, the next step here, and I thought, did they do that all in one step? Yeah, they did. Even hits, it shows it strangely. Now, you have to really be careful here. The only I term here is a minus 16 times 3, which is a minus 48, but they don't do it as a minus 48. They do it as a plus 12 times a minus 4t. Okay? Clever of them, but it's not really obvious why. This to the 3 halves down here, that still works. Okay? Now, here we had a 4j. Okay. All right, here's what you have to do here. On this term, we multiply it by 9 plus 16t squared. So that gives you a 9 plus 16t squared here. That raises this to the 3 halves power. Okay? Multiply 4 times that, and that gives you 36, okay, j. And that's where you get 3 times 12, 36j. So that comes out of the picture okay. But then you have a uh, 16t squared times the times your 4j. And here we had a 16t times 4tj. So that also is a 64t squared j. And this was a 64. This is a minus. That's a plus. Because that's where those went. Those completely disappeared. Magic, but it really did happen that way. Okay? And what you're left with is the nine, yeah, the 9 here, 9 times 3, 9 times 4 is, 9 times 3 is 4. Let's see. These are j terms. This is your 36, and you wound up with a 36 here too. So it's just they've crisscrossed terms and combined them in different ways, skip so many steps, you really do wind up with this. Now, when you take the square, the magnitude of this thing, it's the magnitude of this, which is 16t squared plus 9, we've seen that before. The square root of that, which is in the numerator here. The 12 is out in front, and this thing is, they've rewritten this as this to squared over to the cube power here, which is exactly what this is, the square root of this cubed. Okay, so that's correct. Okay, pull the 12 out. But what you have left here, this is to the 2 halves power. No, this is to the 1 power. This is to the 3rd power. So this one cancels out and leaves you to the 2nd power down here. And the square root of something to the 2nd power is 1 over just this thing here. So that leads to 12 over this thing here. So that is your simplified form of your magnitude of your derivative of the unit tangent vector. Okay? It took a lot of work, but it simplifies like this. So you take this simple form, divide it by this simple form, the 12s will go out, this will go into that, this to the 1 half power, because this is in the 2 halves, that's the 3 halves, so you're left with just 1 over this to the 1 half power times this thing. Okay? And that's, they don't even show that. Well, yes, they will. They're about to show it now. Okay? So it would be this to the 1 half power times that thing there. Okay? So that's your n of t. And what a pain in the neck to get there. Okay? But that's your n of t, and then you plug in t equal 1 and you get this unit vector here. Okay, now, here is the original curve, 3ti plus 2t squared j. When t is equal to 0, you're at 0, 0. When t is equal to 1, you're at 3i plus 2j. Okay? 3i plus 2j. So yeah, you're at this point here. T is equal to 1. And it's curving up like this somehow. Sort of looks like a parabola, but I don't think it is. Okay? It may be in some sense. Okay? And then that's the point you're interested in. There's your t of 1 is 1/5 of this, and your n of 1 is 1/5 of this. Now notice here, you flip the coefficients and change one of the signs. Okay? Which sign do you change? The one that points to the inside. You want the minus 4i here plus 3j. Okay? If you did the plus 4i minus 3j, that would have been pointing this way. That's pointing outside the curve. Your principal unit normal vector always points toward the concave side of the curve. So it must be that one. Okay? But this, it comes out in the math that way for you too. So you usually don't have to worry about it, but when you're plotting it, that's a good check for you to make sure you got it. Looks awfully simple here when you consider all the anguish you have to go through to get that. Okay? Most of the time they're not going to be quite that bad. I found it just incredible. That's the first one they show you. One that's that complicated. Okay? Now, the principal unit normal vector can be difficult to evaluate algebraically. Really, okay, as if that one was just a piece of cake. For plane curves, you can simplify the algebra by doing this. If you've got that unit tangent vector, x of ti plus y of tj, and observing that your n of t must either be, because the dot product of these two has to be 0. So either this one has to be, the y of t is the thing here with the negative x of t there, or the negative y of t here and positive x of t there. Because if you're dotting these two, this one's going to be x of t y of t minus x of t y of t equals 0. This will be minus x of t y of t plus x of t y of t would be 0. So it's got to be one of those two. So if you've got this one, then just change the sign of 1 and flip the 2. Okay? Now, you might ask yourself, how do you know which one it is? What's the one that points toward the inside? So, if you have any clue about what the curve looks like, you have to pick one of these that's pointing toward the inside. Okay? So, because this has to be 1, follows both n 1 of t and n 2 of t are both unit normal vectors. The principal unit normal vector, n, is one that points to the concave side of the curve. So you would choose that one. So you see what you've got here. The 1/5 are the same. Here you got a 3i plus 4j. Here you got a minus 4i plus 3j. Okay? The one that points toward the inside, that's the one you choose. The other one would have been 1/5 of 4i minus 3j. That would have pointed in this direction. That's not the right direction, so you can go to this one. Okay? That's if you know what the curve looks like. Don't know what the curve looks like, gonna have to do some figuring on it. That's about all. Okay? This also holds for curves in space. Those were plane curves. This is a space curve. That is for an object moving along a curve C, which is, okay, this way, coming this way, coming down this way, and down this way, and like that. I know that because unit tangent vector is pointing in this direction. The unit tangent vector points in the direction the object is moving, okay? Whereas the unit normal vector has to be orthogonal to the unit tangent vector. We know that. And points toward in the direction the object is turning. So you see this is turning this way here, so that has a point that way. It couldn't be pointing out that way because this curve is turning in. Now in here, it would be pointing that way because this curve here is turning inward there. The unit tangent vector would be out this way somewhere, and this would be perpendicular to it for the inside. At any point on a curve, the unit normal vector is orthogonal to the unit tangent vector, always. And the principal unit normal vector points in the direction in which the curve is turning. This way here, that way there, and this way here, it looks like it's very slowly pointing this way. Up here, it's hard to tell, but usually you can. Okay? Usually you can. Now, before we go to tangential and normal components of acceleration, let's do example 4. Do we have, yeah, we've got time. Okay, we'll do it on this screen here. Find the principal unit normal vector for the helix r of t is equal to 2 cosine I didn't say t, but cosine ti, plus 2 sine t j plus tk. Yeah, I say tk and write kt. I don't know what's wrong with the brain. Okay. There, I did it again. TK. All right, I think I got it right that time. Got it. Okay, tell me the steps. What do we do first? We're wanting to find the principal unit normal vector of that helix. Find a derivative. R prime of t is equal to negative 2 sine t I plus 2 cosine t j plus k. Perfect. All right. What do we do with that? Find its magnitude. So the magnitude of r prime t is equal to the square root of 4 sine squared t plus 4 cosine squared t plus 1. Right? These two you can combine together and make it 4 times sine squared t plus cosine squared t, but that is 1, so this would be the square root of 4 plus 1 is square root of 5. I skipped a lot of steps there, but you see it? We did it earlier, very similar. Okay? So these two, we factor out of 4, you have sine squared t plus cosine squared t, which is 1. So you have square root of 4 plus 1 is 5. Square root of 5. All right. What do you do with that? Yes, divide them, and that gives you the unit tangent vector, a function of time, and that will be, I'm going to just go put 1 over root 5, I think that's how they did it before, negative 2 sine ti plus 2 cosine tj plus k. I think the last time we did it, we didn't. Oh, no, I think we did have a k in there. Okay. So there's your unit tangent vector. What do you do next? You're looking for the unit normal vector, the principal unit normal vector. Okay? So how do we do that? Take a derivative of this. Okay, and it's no longer necessarily going to be a unit vector, so I'll quit putting the hat over it. Now, I'm going to keep the 1 over root 5 out front. And what will this be? Derivative of that will be negative 2 cosine t I minus 2 sine tj. Done. Because that derivative is 0. Derivative of 1 is 0. Okay? Now what? Same step as before. Take the magnitude of this first derivative of your unit tangent vector as a function of time. All right. So let's just keep the 1 over root 5 out here and then do the square root of this. And what would that give you? Minus 4 cosine squared t plus, well, actually it's going to be a plus, yeah, plus 4 sine squared t. And what is that? Okay, and that gives you root 4 times 1, and root 4 is 2, so this is 2 over root 5. So there's the magnitude of that unit tangent vector. Okay, what do you do with that? No. The unit normal vector, that's what we're looking for. Whoops, unit normal vector. I like to put the housetop over it. This one's much easier to do than the last one. Unit normal vector as a function is the, right here, t prime over magnitude of t prime. Okay? Now, t prime is going to be 1 over root 5 times minus 2 cosine ti minus 2 sine tj. Okay? Divide that by root 5 over 2, which is going to move the 2 up here, and the root 5s disappear. No, I didn't do that right. I divided by the wrong thing. Okay, let me start that one over again. Okay, that was a 1 over root 5 here, and divide it by 2 over root 5 here. The root 5s go out, that's how I should have written, and you have a 1/2, but the 2 will cancel out these 2's, and you're left with the unit normal vector is negative cosine ti minus sine tj. Sorry, I ran out of room there. Okay, and let's see if that's what they got. Yes, look at that. They got the right answer here without nearly the pain and agony that we did last time. Now, what this says here is that the unit normal vector always is in the xy plane. This helix is going up, okay? It's a spatial foot, but the unit normal vector is always pointing toward that z-axis. Wherever it is, pointing toward the z-axis, and it's that unit vector that does that, okay? As your t's vary, it goes around, okay? Now, all right. Now we have a little bit of time to get started on tangential and normal components of acceleration. In general, part of the acceleration acts in the line of motion, and part of it, the normal part, acts perpendicular to the line of motion. In order to determine these two components, you can use the unit vectors t of t and n of t, unit tangent vector, unit normal vector, principal unit normal vector, which serve in much the same way as I and j do in representing vectors of the plane. The following theorem states that the acceleration vector lies in the plane determined by these two, the unit tangent vector and the unit normal vector. The acceleration vector has to be in that plane. And this theorem supports that. Acceleration vector is R of t is the position vector for a smooth curve C, and n of t does exist. Then the acceleration vector A of t has to be in the plane determined by the unit tangent vector and the unit normal vector. And basically, let me give you this, okay? When an object is moving, okay, its first derivative is how fast it's moving. Its velocity. Okay. The second derivative is how fast the velocity is changing. Okay. Now, velocity can change. It can be one of two ways. It can be increasing in the velocity, and therefore it's accelerating, or it can be changing direction. The change of direction is made by the unit normal vector. The change of acceleration is made in the direction of the change of speed in the direction of the unit tangent vector. So therefore, the total acceleration has to have one component this way and one component that way. So it's increasing its speed and changing its direction. Okay? So they have to be in the same plane. Now that's sort of the physics side of it, but it's, to me, that helps it make a little more sense. So the coefficients of t and n, unit tangent vector and unit normal vector, in the proof of theorem 12.2 are called the tangential and normal components of acceleration. And here's how, and we didn't do the proof, the slideshow didn't show it. If none of you are math majors, right? Okay. You can go back and look at that. But the tangential component of the acceleration vector is merely the first derivative of the speed. That's in the direction of the velocity vector, and it's how fast that velocity vector is changing. So yeah, that's the tangential component of that. The normal component, the a sub n, that would be this velocity vector times the magnitude of what, and these are components, so these are scalar quantities, okay? Magnitudes of velocities are still scalar, okay? Magnitude, that's the speed, times the rate at which the tangent vector is changing, the first derivative of the unit tangent vector, that will give you that component. So you can then write the acceleration vector is this a of t times the unit tangent vector plus the a sub n times the unit normal vector. Now this is kind of a pain in the neck to get. So there is an easier way to do that, and they'll tell you that in a little bit. So the following theorem lists some convenient formulas for a sub t and a sub n. Okay? Now again, those are these things here. Now they write the subs as if they were vectors, and I usually do put housetops on them, but that doesn't mean this is a vector quantity. It's a scalar quantity. Those are scalars, but it's in those directions. Okay? So here's what we got. If R of t is the position vector of a smooth curve C, for which n of t does exist, the unit normal vector does exist, then the tangential and normal components of the acceleration are as follows. Now, keep in mind that we've already done most of this stuff before. Okay? The a sub t, the component of the acceleration vector in the direction of the unit tangent vector, is, just like we said, is the first derivative of the speed. Now, you write that as a function of t, the magnitude of your velocity vector, okay? And take a derivative of that. That could be a pain in the neck to do. We've just seen taking derivatives of square roots really get messy. Guess what? The likelihood, if you got the r of t, taking a derivative of that gives you v of t. Take a derivative of that, and you get a of t. So this is an easy thing to get. Okay? Now, the unit tangent vector is not really all that easy, but guess what? Okay? The unit tangent vector is the velocity vector divided by the magnitude of velocity vector. So guess what? You've already got this. To get this, you had to get this. So all I have to do is take the magnitude of that and then dot these two, divide by the magnitude. Now that is usually not too bad to do. Because the first thing you do is take the derivative of this, that gives you the velocity vector. Take the magnitude of that, that gives you this. Take the derivative of the velocity vector and you get the acceleration vector. Take its dot product and divide by this. That's the easy way to go, just about every time. Okay? So, how about the unit normal vector, the component of the acceleration in that direction? Well, this is okay, you already had figured this, so that's not too bad. But this is a lot of work to get that. You have to take the derivative of your unit tangent vector, which is this thing, which we haven't really done. That's the velocity vector divided by the magnitude of velocity vector. So that's sort of a pain in the neck. And then take a derivative of it, and then take a magnitude of that. But guess what? That is A, which was just the second derivative of the displacement vector by n. Yeah, the n was hard to get. But guess what? This is A, V cross A. You already have V, you already have A. V cross A is easy to do. Take the magnitude of that once you've done it, divide by this thing you've already done a dozen times. Okay, that could be a pain. But guess what? There's yet an easier way. You already know what the acceleration vector is. You did that up here and here. Okay? Take its magnitude and subtract from that this unit tangent vector, which you had right here, squared. Square root of that, that gives you your unit, your acceleration, the normal component of your units of your acceleration vector. This is the easy way to do this. This isn't too bad, okay? But this is even easier, okay? Note that if a sub n is greater, the a sub n always has to be greater than or equal to 0. Obvious, well, it's not obvious, I guess. But you see, the acceleration vector minus this component here, it's got to be a positive number because this is the component vector, okay? And then take the square root of it, it's got to be greater than 0. Unless these two are the same, and then that would be 0. The normal component of the acceleration is also called the centripetal component that pulls you inward. That's your turning acceleration, and the other one is your tangent speed. Okay? So, do we have time to do example 5? Some of these are a little long, but I don't think example 5 will be. Let's do it. See if we can do it quickly. Or do you want to? I think we got, what, 10 minutes? Huh? What's that? Oh, okay. Well, you can pick it up on the video. Okay? Let's see if we can do it. Example 5. You can also see larssoncalculus.com for an interactive version of this. So here's your vector. R of t is equal to 3ti minus tj plus t squared k. I don't think this will be too bad. Guess what the first thing we'll do? Take a derivative, r prime of t. And that's going to be, second? You said 3, right? Okay, 3i minus j. Okay. Okay. Perfect. Okay. Now, remembering back, what we need is, looking just at the top of the page, to get the tangential and normal components of acceleration for the position vector, you need v of t, which we have. This is your v of t. That's the first root of the unit tangent vector. You need a of t, so let's go on and do that. A of t, let me write it out a little differently. A of t is equal to V prime of t, which is equal to R double prime of t. So what would that be? I don't think so. Derivative of 3 is 0. Derivative of minus 1 is 0. This will just be 2k. Perfect. Okay. You need your A vector. That's pretty easy to get. Looking up there at the top, you need the magnitude of V. So let's do that one. Woo, where did that come from? My pen just decided to change on me. Okay. And it still decided to change on me. There we go. We got it back. The magnitude of V of t is equal to what? Yeah, 3 squared is 9 plus 1 plus 4t squared. So this is equal to the square root of 10 plus 4t squared. Oh, boo hiss. That's kind of messy. Okay? But we need it. Okay? Now, your A of t, your A sub, what are we looking for? Tangential component. I'm going A sub t. If you remember what that is, that's V dot A divided by magnitude of V. And we got all the pieces up here. Right? There it is, top of the page. Oh, and this. Okay, yeah. No, I'm sorry. Yeah, that's right. V dot A divided by that. Okay, V dot A. Remember how to do that? You multiply component by component. 3 times 0 is 0. Minus 1 times 0 is 0. And 2t times 2 is 4t squared. That's your numerator. And then your denominator we just got is the square root of 10 plus 4t squared. Okay? That is your tangential component of the acceleration at any time t. 4t over the square root of 10 plus 4t squared. That's pretty straightforward, isn't it? Okay? Now, they take you through what I think is the longer way to do it. I think the shortest way to do the A sub n, do we have time? Oh, we may not, do we? I don't think so. All right, let's just say that we're going to pick up next time, and somewhere I thought I had a pencil out. There it is. Okay, we're going to start out with the n component, okay? But frankly, I'm going to do it down there, okay? Because that's so much easier to do than the other. Now remember, these are components. They are not vectors. That's why you lost your n, and that's why you use dot products and magnitudes. There are no i's, j's, and k's in these components. Okay. So, let me mark my spot here. Oh, we came so close to finishing. Do any of the odds 3 through 7? They're all at Calc Chat. 5's at Calc View. Do any of the odds 9 through 13? They're all at Calc Chat. 9's at Calc View. Do any of the odds 15 through 19? They're all at Calc Chat. 15's at Calc View. Do either 21 or 23? They're both at Calc Chat. And then start doing 25 through 39, the odds 25 to 39, they're all at Calc Chat. 27's at Calc View. And we'll pick up the rest of those next time. Okay? All right. We'll finish 12.4 next time and get started on 12.5, 12.5 is a little on the long side, but I think we can finish. And when we finish 12.5, we're through with chapter 12. And then you'll have the test on 11.6, wasn't it? And then the 5 sections of 12. Okay? What's that?
You'll give us the test Wednesday.
Yeah, I'll give you the test Wednesday. Say again? Yeah, you have at least a week to complete it. Yeah. That's why you can ask me questions on the following Monday if you have any, and you still got plenty of time to work on it. And you got a weekend to work on it, so. Yeah. All right, good deal. I'm so sorry. I was running out of energy. I'm going to do this most days, I think, because I don't have time to eat lunch, and I'm losing it fast. Sorry about that.